Hey there, welcome to a video discussing the second half of the 3.1 notes. Here we're going to talk about the bottom of page 3, the relationship between the graphs of f of x and f prime of x. These could be a little tricky, so be patient here and definitely prepare some questions so we can discuss them on class later this week. So remember, the graph of f prime is always the graph of the slope of f against x. So what does that mean? Let's look at the graph of f to the right. Sorry, to the left. The graph of f to the left. We notice that we have a piecewise function, and each of these piecewise functions are linear, each portion are linear in nature, right? So we have like 5 different parts here, and we have 5 different intervals, of course: negative infinity, negative 4, negative 4, negative 2, negative 2 to 2, 2 to 4, and 4 to infinity. So let's investigate each of these portions here and find their slopes. So if you look at this one, it looks like this one goes down 1, 2, 3, 4, and right 2. So it's probably a slope of negative 2 there. The next one probably goes up 2 and right 2, probably a slope of 1. That's flat, slope of 0. 2 to 4 looks like it goes down 4 and right 1, so negative 4. And this one here looks like it goes up 2 over 1. Let me look at that, if I'm seeing that correctly. No, it looks like it's probably going up 4 over 1. Yeah, so it's probably positive 4. We'll say that. Or actually, let me take that back again. So that's definitely negative 4. It looks like this is actually going up 3 over 1. So we'll say positive 3. Okay, so what you do is in your graph f prime, what you're doing is that these right here become the y values on the f prime graph. So that's what's meant in that bullet point right above. Remember that the graph of f prime is the graph of the slope of f against x. So from negative and negative 4, you have what you're going to graph y equals negative 2. So you're going to graph this, and it's going to be an open circle because we're doing it for an open interval from negative and negative 4. And I'm not really sure what the slope's going to be at the corners. So basically the corners will be holes on the f prime graph. Because we're doing this for open intervals only. And then obviously I'm going to graph this one, y equals 1 from negative 4 to negative 2 for x. That should be open. Then 0 from negative 2 to 2. Negative 4 from 2 to 4. And then positive 3. And then forever. So that's how you graph f prime when you're given the graph of f. Let's look at another one on the next page. This one's not going to be piecewise, it's actually going to be a smooth polynomial function. Let me clear my drawings. Move on to page 4. So again, you're supposed to graph f prime. We'll do it right below. Now remember, f prime represents slopes of tangent lines. For graph of f. So you have this, and this, and this, and this, and this. So you have all these different tangent lines here. You're going to have to kind of estimate what's going on. So let me draw it again. Sometimes it might help to even have a ruler. I won't quite do that, but if the xy at A is negative 4, at B the xy is negative 3, at C is negative 2, at D looks like it's 0, at E looks like it's 2, F looks like the xy is 3, and then xy at F is, or probably we'll call this G, it's missing, we'll call that 4. Then what we're going to do is we're going to find the slope of the tangent lines at each of those points. So again, these are going to be estimates, just so you know. So the first one definitely looks like a positive slope, and probably maybe up 4/1 maybe. At -3, it's not as steep. We'll probably say about 2. It's definitely flat. Usually that happens when you have a peak. Negative here will say it's -1. Definitely flat over here will say it's 0. Definitely positive here will say about, we'll say 1. And then at G, we'll say it's about 3, let's say. So again, these are just estimates. So what you do then is you plot these points, -4, 4, -3, 2. Remember, these are now y values on the graph of f prime, which we're doing right here. -2, 0, 0, -1, 2, 0, 3, 1, 4, 3. So here's something that kind of looks like that. And what's interesting is that this kind of looks like a cubic function. This kind of looks like a quadratic function. We'll kind of revisit that in a little while once we start doing more analytical techniques for derivatives. So let's look at the bullet points right below. So what can you see about the y values of the graph of f prime when the y values of f are increasing? So when the y values of f are increasing, as we saw here, so again, what can we say about the graph of f prime? So basically, this portion right here, y is increasing. Likewise with this portion over here. Whereas for this portion, y is decreasing. And we notice that the slopes were all positive. These have positive f prime values here, likewise over here, because the slopes are positive for the tangent lines. And remember, the slope of the tangent line is a derivative. And these had negative f prime values. So going back to those bullet points again, what can you say about the y values of the graph of f prime when the y values of f are increasing? F prime is going to be positive. So that means that the y values of f prime graph are positive or above the x-axis. Whereas here, when you have a decreasing function, like when the graph is dropping, f prime is negative. So the y values of f prime graph are negative or below the x-axis. That's what I say there. And then what happens when we have a horizontal tangent? So we have like a peak there. Well, f prime is going to be 0. And again, the y values of that prime graph are 0. And they happen to be just on the x-axis. What this tells us is that the x-intercept of f prime graph will probably represent a max or min on the f graph, the original function. And we're going to definitely, that's going to be a key part of what we do this semester, is talking about that. And I'll make sure I mention it often in class. Okay, let's try this again for example 6. Match the points of the given slopes. So for example, which one has a slope of -3? Probably f, I'd say. The slope of -1, probably C. The slope is 0, probably at a peak like E. 1/2, probably A. I mean, B is a little steeper and D is a little steeper, so I'd probably say A there. The slope of 1, between B and D, I'd probably say B because D seems to be more steep than the slope of B. So that's how I'd match it up. Okay, let's go to page 5 of the notes. Now for page 5 of the notes, we're going to be talking about one-sided derivatives. And this is what I got confused with the square root of x when I was saying it was the two-side limit existed when only the one-side limit existed. I was thinking of this stuff here. So when you have endpoints, you can tend to use the appropriate one-side derivative to find the derivative at endpoints. Now there's something called a right-hand derivative. Remember, we had the limit definition of derivative right here, which we've talked about already in section 2.4. And of course, beginning of this section. But this is when h is approaching 0 from the right. So remember, here's A, here's some funky curve, here's A plus h. We want h approach 0, and if we're coming from the right side, so h is positive, then obviously you're coming from the right side of A, so we call that a right-hand derivative as this point gets closer and closer to A. Whereas here, we call it the left-hand derivative. I'll call RHD and LHD, just like we did RHL and LHL for right and left-hand limits respectively. But sometimes you have so you have the same kind of curve. Here's A. Let's say h is right here. So now h is going to be negative. It's going to be, so you're doing A plus h. You're coming at from this direction, it's A plus h right there. Now h is less than 0. So we call that left-hand derivative because we're approaching A from the left side. A function is differentiable on the closed interval from A to B if it has derivative every interior point. So if you think about the open interval, so not including the endpoints, every interior point of the interval, and if the appropriate one-side derivative exists at the endpoints too. So in this case here, you're asked to sketch a graph of f prime. So just find the slopes. That's 3, that's 0, that's -1. So of course I have this, and it starts at -4 and goes to -3. And then from -3 to 4, you have that. And then down below, you have that. So that's how you do that graph. Now let's look at a piecewise function down below. And we have a worksheet on this that we'll probably hit up on Thursday or the week after. We'll clear my drawings. So you're asked to find the one-side derivatives, or use one-side derivatives, show that this function does not have derivative x equals 1. Well, let's graph the piecewise function first. So if I plug 1 into here, I get 2, but it's going to be a whole. And it's 2x squared, so if I just kind of do everything else, I think it's way up here. It goes on forever. 5x minus 3, so x is greater than or equal to 1. So if I plug 1, I still get 2, so it is continuous, for sure. Definitely is continuous. And slope of 5, so up 5 over 1. That makes sense. So you have that. And remember that the whole is filled in. So it's definitely continuous, but one thing we're going to talk about 3.2 is that continuity does not guarantee differentiability. We'll have that discussion 3.2 on Thursday. Just because you're continuous doesn't mean your derivative is going to exist. So what you do is you find the LHD and you find the RHD. So LHD we write like this. The limit is h approaches 0 from the left side of your function. So f of a plus h minus f of a all over h. Now, a is 1. And if I plug in, and remember h is less than 0, so if you're doing 1 plus h here, 1 plus a small negative number, clearly I'm less than 1, so I'm going to be using this function right here. So when I evaluate it, it's going to be 2, 1 plus h squared minus f of 1, which of course is just using that one because 1's included there, 5 times 1 minus 3, all over h. And again, the limit as h approaches 0 from the left side. We'll have to clean it up. There's quite a bit of messy algebra. So I'll have to FOIL this and distribute the 2. So just bear with me. It's going to be 2 plus 4h plus 2h squared. So what I simultaneously did is I FOILed 1 plus h with itself and then distributed the 2. And 5 minus 3 is 2, so minus 2. All over h, cancel, cancel. The limit as h approaches 0 from the left. Now, you can actually do a little reduction, factor out h, 4 plus 2h over h, those cancel, those h approaches 0 from the left, plug in 0, you get 4. So basically the slope of the tangent line right before we get to 1 is going to be 4. Now for right-hand derivative, I'll do green for a little contrast. You're doing the limit as h approaches 0 from the right side, so h is 0 plus. Again, f of 1 plus h minus f1. I mean, you can say a plus h minus f of a, but we know a is 1, so it's kind of redundant to say that. Now remember, 1 plus h, basically what you're doing is you're doing 1 plus a small positive number. So it's a little bit more than 1. So I'm going to be using this function right here. So if I plug that in, I can do 5 times 1 plus h minus 3 minus f of 1, which I know is 2, all over h, the limit as h approaches 0. So that's 5 plus 5h minus 5 over h. Those cancel. And we're at 0 plus, 0 plus. So you have 5h over h, which of course reduces. So it's just 5. But here's the problem. The LHD does not equal the RHD, right? 4 does not equal 5. Hence, that's how you prove that's not differentiable. So f prime of 1 does not exist because the LHD does not equal the RHD at x equals 1. That would be your final conclusion for that one. So you'll have some practice with that on the homework, and we'll do some worksheet stuff on that as well. Lastly, let's look at page 6. So now you're kind of going the other direction. Now you're given the graph of f prime, you have to give the graph of f. So sketch your graph of f given f prime. Well, you've given one condition that f is 0 equals 0. That's easy. That's 0 comma 0. The third condition, just make sure there's no breaks in the graph. Just keep that in mind. And here you have this right here. So these are slopes of tangent lines. And because you have these holes here, we're not going to be differentiable at x equals 1. In fact, we're going to think of it as a corner. And we're going to talk about that in more detail in 3.2. That'll give rise to a corner. So it's going to have a slope of 2 here. And, because that's the y, remember the y value on f prime graph is slope of tangent line. We know this. We've talked about this already. So you have a slope of 2 here, and you have a slope of -1 here. And actually, I could draw a slope of 2 a little better. That was pretty bad. I can do better than that. And there we go. So again, one strategic tip is, find an interval containing the given point. Oh, wait one sec. I kind of messed it up. Let me backtrack a little bit. It's not different to x equals 1. You're going to have the corner there. My apologies. So at 0, 0, the slope is supposed to be -1. So it's supposed to include it, and then we're supposed to go over here and then do this. My apologies. So the interval here is from -infinity to -1, we have that slope, and here from 1 to infinity, we have that. So there we go. Okay, so that concludes the second half of the 3.1 notes. There'll be a Google form to answer the homework as well as some textbook problems.